Hi, today we are going to learn about logic. And of course, I know your response will be like, oh, I'm logical person. I know how to think through things. I know how to respond. I know how to deduce stuff. But we will see in this in a moment whether you are actually logical or not. And in this lecture, this lecture is divided into 4 main parts. First is about the definition, the motivation on why we study logic in the first place. Second is about the math part. Once you define something in math, then the next question you ask is, can you combine things? Can you separate things? Can you give some extra or some special definitions to things? That's the mathy part. Next is about the equivalence, meaning that how do we know whether two statements are the same? Whether I like math and I don't dislike math are the same. Logically, we will learn this in this class. And lastly, we're gonna learn about the quantifier. That's a fancy word of statement in the form of everyone, blah blah blah, or nobody. What I mean when I say everyone loves math, or nobody hates chocolate? Can you tell if my statement is true or false? Can you prove it or can you disprove it? That's what we are going to see in this class. But first, let's start from the definition of logic. So, yeah, logic. Let's take a look at this image again. Oh, and if you have a copy to the slide, you can go to the link to the official page for that. So let's start from a math joke. So it starts by saying that 3 logicians walk into a bar, and these logicians, you might think of logicians as people who deal with like electronic circuits. I think there's a word for that. I'm not sure if it's like logic. Like something. Not sure about that, but in this case, this means people who study logic. People who study logic. How you know? Those math people. Like the one who is talking on the screen right now. So 3 logicians walk into a bar. And then the waitress, the person in red, asks, does everyone want beer? So let's focus on this question. Does everyone, that's the word, everyone wants beer? And interestingly, the first person say, I don't know. Which is weird, like, because usually when someone asks you the does or do question, your response should be yes or no. But he says, I don't know. And then, again, the second person follows suit and say, oh, I don't know either. But that person says, yes. Can you see what's going on here? Are they crazy or are they doing what people should do? Should respond to this kind of question. Let's first focus on the question. Like usually, like I would ask, like if it's me and you, I would ask you, 101, do you want beer? Do you want some beer? And you will say, okay, yes or no. And that's already the only 2 acceptable responses, because you know what you want. But by the wording of this question, like the waitress asks 3 people at the same time. They ask whether every single one of them wants beer. And let's start the trend. The person said, I don't know. Let's think about it. Can he respond yes? What happens if he responds yes? Or what happens if he responds no? If he responds yes, it means that he knows. It means he knows all 3 people or 3 logicians want some beer. And that's not the case, like, because he's the first to respond and he doesn't know about the opinion of others yet. That means that's not possible. He cannot claim he knows what other people want. So this is cross out. But what about no? What happens if he responds no? If he responds no to that question, it means this question is false. And then you have to think about it for a moment. What it means for that to be false? If it's false, it means not everyone wants beer. If he responds no, that will imply this statement. But then again, he doesn't know what other two people are thinking, so he cannot exert his opinions onto those two people. And that means if he answers no, that means not everyone wants beer, and not everyone wants beer. That implies that someone. We will learn about that in the last section. Someone doesn't want beer. And these two statements are equivalent. They mean the same thing. Just have to think about it for a moment. If not everyone wants beer, then some of those people want. And who doesn't want one? How does he know that someone doesn't want one? Again, he doesn't know. He only knows himself. That means if he answers no, it implies that he himself doesn't want it. That's all the information he has at hand. So, from this statement, from this response, if he said no, it would have mean that he doesn't want what. So we can finally deduce that because he responds, I don't know, it means he does want it. He does want. And since he wants it, and he doesn't know about other people, like the only logically correct response would be, I don't know. But then, since other people are also logicians, like they know perfectly well what he meant by that. So they both know, oh, that means the first person wants some beer. And then, the first person wants some beer. Let's make a tick mark on that. And then the second person answer the same way. He says, I don't know. Again, that implies that the second person himself also does want it. Because he doesn't know about the third person yet. And lastly, the third person, knowing that the third two want some beer, he now can answer with confidence that yes, all three of us want beer. Everyone wants beer. But that's how you can deduce this kind of statement. You can say it's short, right? But again, that has some information that these people didn't know, at the time when they respond. So if you think you are logical, and then whenever you are asked this question, does everyone want something? The response should be, I don't know, or no. If you know that you don't, then you can say no. Not everyone wants it because I don't. But otherwise, that's how you are supposed to respond. Is that good? Yes and no. It depends on how you view the language. Because usually, when people use language in everyday life, you don't expect them to ask you sophisticated questions. But you don't expect them to ask for the details that math people use. Usually, he meant that, oh, do you want beer? But since there are three people on the same table, she has to include everyone. And that's what happened. Oh yeah, you should also notice her facial expression. So that's how you can interpret or understand that joke. And this took about 8 minutes to explain. But anyway, we will go into details more on how to interpret this kind of statement and how you can disprove that. And this is one kind of logic where you have to be be exact about wording, exact about the value, whether it's yes or no, true or false, correct or incorrect. But there is actually another kind of logic, which is more common. I think when people think that, or when people claim that they are logical, that they think about the Sherlock Holmes type logical thinking. And in logic, there are two branches. Or let's say there are two types. First is the deduction on the left, which is associated to Aristotle, or math or philosophical person. Philosophy. This is what we call deduction, and the other type is the induction, which is about the Sherlock Holmes. Or you can see the images or the icons inside. Oops. There's some kind of magical instruments, cameras, data, art. It's also logic, but it's a different way to give a reason. So for the Aristotle, maybe I say we because I'm also part of this branch. You start from a theory. For instance, let's start from numbers. We have numbers. 1, 2, 3, 4, 5, 1 half, minus 10, pi e. Yeah, there's lots of numbers. We define numbers, yeah, where we can, do. You can measure, you can compute. Let's use this in. Suppose we start from real numbers. We define real numbers. They are numbers that we can measure, we can compute, then we can write decimals. Then we have some kind of hypothesis about those theories. Like for instance, I might ask whether the product of two real number is still a real number. This may be my hypothesis. And then I need to use some observation. Instead, I can try 2 times 3, 1 half times 3/4, pi times e, and so on and so forth. I can use lots of observation to see if the pattern persists, or if there is any breaking change, or any counter example. And then it should be like some kind of like proving theorem. Once we have some observation, then you have to prove. And I think it's proof. You confirm it by proving, like making logical statements, a sequence of logical statements. Like for instance, you have to define as a be real number, let's be real number, then we define a times b as blah 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 blah, and then you can conclude that, and then you write QED. This is what we see, what we usually see in math proof. This is the type of deduction, starting from a theory, starting from the fact or the truth of the universe, and then see some pattern. But on the other hand, another way of reason is called the induction. You use induction is to the Sherlock Holmes. Because the Sherlock, even if like you are Sherlock Holmes, you wasn't at the crime scene in the moment it took place. So what you could do is you start from observation, and you went to the crime scene and see if there's anything interesting going around. Are there bloods, are there crops, are there weapons, for instance? And then you see a pattern, and you start to draw some lines. Like you may have seen this kind of meme where people draw have a lot of things on the board, and then you draw lines. Make like conspiracy theorem, that kind of thing. And then once you see a pattern that you can link, these two events must happen at once. There's a blood stain on the weapon, and the blood is from the victim. So that means this victim was killed by that weapon, for instance. And then once you get a pattern, then you start from the hypothesis. This must be the weapon. This is a murder weapon. And then you find more proof. and you establish that at the end Arrow's theory. And you can conclude that, oh, that means this person is killed by this weapon, and this weapon is from someone else, so that person might be a murderer, for instance. So these are two opposite kind of reasoning, and it is easy to mistake one from the other. So you can see that they have some common parts. You observe, you have hypothesis, you have theory. The start, where you start? Do you start from what you know, or do you start from scattering information and then try to assemble them back into a big picture? So these are two types of reasoning, and you can guess what we are going to learn in this class. Is on the left part, we are going to deduce stuff. We're going to start from some statements, some theorems, some symbols, some definitions, and see if we can work with that. Oh yeah, some examples of deductions. Or maybe I should start from here. Like if the deductions, the math part on the left. For instance, if A equals to B and B equals to C, then A equals to C. So the first two parts is they are kind of we have to start from actually the definition of what it means for those two things to equal. We have to define, we have to have the theory about the equal sign. Two things are equal when they are equal. I mean, yeah, it's actually impossible to define if you don't know the formal math jargons. But let's say, suppose you know about equals. Oh, yeah, two things can be equal. And then you start observing that, oh, if two things are equal, if the first thing is equal to the second thing, and the second thing is equal to the third thing, then the first thing and the third thing are also equal. Maybe it feels obvious this way, but let me use. So like if you know this box has the same weight as that circle, you know that circle has the same weight as this triangle, then you can conclude that the square and then the triangle has the same weight as well. So now it's not obvious that you are comparing 5 to 5, comparing weight of different shapes. And based on this theorem about equal sign, and based on facts, based on the hypothesis we have, then we can conclude, we can make an observation and conclude that, oh, the first object and the third object must be equivalent, they must be equal. But that's one type of deduction, just in pure symbols. Also, in the second example, you can say that, okay, all squares are rectangles, and all rectangles have 4 sides, and all squares have 4 sides. And it's more common in logical deduction. You start from 2 statements or 2 sentences. You can conclude anything. Notice that there is no equal sign or any of those things at all, right? There's a word are, the word have, the word have. So in a sense, you have to translate that into a mathematical or a logical statement first. In this case, if you know how to do that, then you will translate that to P then Q, and then Q and then R, and you can conclude that P then R. But again, it is hidden in the structure of this sentence. Okay, so that's deductions in math. We have all the information. We just have to draw the conclusion from all these facts. But on the other hand, like for inductions, you start from observation. In the first example, Ray is a football player. You know that all football players weigh more than 170 pounds. Notice how I use the word pounds because American textbook. Then you conclude that Ray weighs more than 170 pounds. Right? And usually this could be correct or incorrect, right? Depending on whether this one is fact or is observation.
And this is
What we have to settle first. Like, is that fact? When you declare that all football players weigh more than 170 pounds, does it mean that you have the spreadsheet of all football players and have all their weights, and you notice that they all weigh more than that? Or you made some observation, oh, I know 5 football players and they all weigh more than 120 pounds. So I believe, or I guess, that Ray must also weigh more than 120 pounds. And that's the inductions. Like, because again, eventually we still don't know yet whether they how much Ray weighs. We don't have information. We could ask him nicely, or we could put him in a box and weight him forcefully. But as of now, like this, based on the information we are given, this is what we can conclude. And yeah, well, maybe the second one is also it's a good example of something that sounds right, but it's obviously wrong. So for instance, all cars in this town, let's say in I was about to say Bangkok, but it's not. All cars in the US, I drive on the right side of the street. Street?
And they all right. Oh,
that's not right. Right? Yeah, this means that. And I don't think that's how people drive in Bangkok. But I suppose they drive on the right side of the street. And here is your observation. And then you conclude immediately that, therefore, all cars in all towns, that's a strong statement, like all towns, must drive on the right side of the street. And we can see right away that this sentence or this conclusion is false, because we have at least one counter example, which is Bangkok. If you are close to the street, you can just look outside and see, oh, they drive on the left, not right. But this toy is wrong. But nevertheless, this is kind of inductions. Because the author or the person who claims this doesn't have enough information on about the where people drive. So he could say that he did his best. Oh, that's lots of examples. He saw hundreds of cars. So he assumed that every single car must be in the same category, but it's not. These are the two different types. And again, we're gonna focus on the first part where we can say something for sure, not up to chance. If you want deduction, then I think you can read some deduction novels. What kind of that? Detective novel. Sorry, not deduction novel. Oh, it's a read induction. Detective novel. In this class. Okay, but before we start the topics, yeah, we have to first start from the definition, what it means for something to be logic, and what it means for these sentences, because we see lots of sentences, right? And the first thing we have to ask is whether it's true or false, so we can believe it or not. So we start from the first definition, which is the proposition. And you don't have to remember this word because we're gonna discard that pretty soon. Right? But it's just a statement or a sentence or something people claim. And the statement is a proposition. Like if it's a statement, then it's either true or false. You can say anything. You can claim whatever you want to. But what you claim, like, it's classified as a statement or as a proposition only when we can say it's true or false. And if it's true, then we say it's true, and we denote that as a single letter T. If it's false, we denote as F. And this true and false are what we call the truth value. Because in language, you say it's true or false, but Those are just like two words.
And
So we need to make it a value. And once it's a value, you will see in a moment when it's a value. We can compare value, we can combine values, we can do lots of things with values. So now each statement has a value on it. It's either true or false. For instance, if we have both statements, not is the opposite of south. Yeah, that's a statement. We can prove or we can determine whether it's true or false immediately. I did that, it's true. Oh, the next one is the standard of playing cards has 44 cards. And again, it depends on the structure of the sentence. Now, in this case, it does specify that we are looking at standard deck of playing cards. Like not any card, but if you talk about cards, then you can think of like credit cards or anything like that. But no, this is the standard one. There should be only one standard, like because it depends on cards. But yeah, if we are talking about the same deck, the same standard deck of playing cards or poker cards, it's supposed to have 54 cards. Because in those cards they include jokers, which I think we rarely use. If you are serious about playing cards, we only rarely use those cards. It's 52. So that's true. The third statement is yeah, false. Focus on the math statement that we can do. And then there's a fourth statement. This is an interesting thought experiment. The question is, does that statement a proposition or not? Can we say whether it's true or false? Yes, we can. The thing is, yes, we can, but yes, we can. It is either true or false. The statement itself has a truth value. The statement itself has a true value, but we don't know whether it's true, whether it's true or false. Think about it. If we have enough resources to explore the whole universe, we would have been able to answer this question, right? If we had enough resources and time to explore the whole universe, we could determine that. But we don't, so we can't. But if we could, but like, in theory we could. Like, in theory we could say whether it's true or false. There's no third option for that. So this qualifies as a question. We just don't know whether it's true or false, but it's one of these two options. Sounds weird, right? But that's how it is. So we have the proposition and the truth value. These are the two definitions. And yeah, if you can assign a truth value, then it is not a proposition. For instance, Jansung's homework is fun. It depends, right? Because I know that if two people are asked this question or they are given this proposition or they are given this statement, right? One might agree, one might disagree. So this is about opinion. It could be fun for me, but not fun for you. It's fun, right? I think. Oh, the second question is x squared equals to 3. It looks like a proper mathematical statement, right? But the thing is, we don't know x yet. Okay, we say something is equal to 3, but what is that thing? What if I say the value is 3? You might ask, what value of what? Something is missing from that statement. Something is missing from that sentence. It's incomplete. So it's not a proposition because it has a variable. And lastly, life is meaningful. And this is kind of an opinion on one hand, so it's not a proposition. On the other hand, that this is kind of let's say ambiguous, not well defined. We have to define first what is life. You may agree that we are talking about human's life, but again, it doesn't define that. And then what it means for something to be meaningful. It means you have to live at least 20 years. You need to make a breakthrough. You need to make enough money to do stuff. You need to have kids. You know, this can mean lots of things. And so it's not even an opinion. It's just not defined. We just disregard that and leave it to philosophy or people to argue about that. But in this class, we're gonna focus on things we can say for sure whether it's true or false. And yet, there's one short exercise for this break. Come up with 3 propositions and 3 non-propositions. And that's the end of the first section.